Greetings everyone, we are team ctrl+alt+first and we are here to present a solution for the problem statement SIH'25 Smart Traffic Management System for Urban Conditions. Every single one of us has experienced the frustration of being stuck in traffic, wasting time, burning fuel and contributing to pollution. This isn't just an inconvenience, it's a massive drain in our economy and our environment. Our solution directly tackles this problem by creating an intelligent adaptive traffic grid for our cities. Let's show you how. Here's a look of a real-time dashboard wherein we feed the CCTV camera input to YOLO, recognize the vehicles and let the RL agent take the decision. This is a visualization of what is sensed by the camera with the bikes, cars and people walking being put up on the dashboard and a live monitoring of the number of vehicles out of the total capacity that each road can have being displayed on the right. And these are the four metrics which we have to evaluate the traffic that is currently present there, and we train the RL agent based on this. Finally, we have a graph for each metric showing us how it is being optimized in real time. So here's a prototype that we developed where we have a single junction and an RL, DPU network in this case, takes the decision of shifting from red to green in appropriate junctions as per the reward function that we have here, which is the least congestion time. You can see that as vehicles start to stagnate, it understands that the reward goes down and it turns on green for whichever direction there are more vehicles. We will be developing upon the same by having a YOLO model on real-time camera feed, where the data taken from here as traffic simulated from Sumo will be directly data fed from CCTV cameras. Our solution is a three-layer intelligence system designed to see, think and act. First is the vision layer. This is what our system sees. It utilizes a state-of-the-art YOLO-based detection model running on existing live camera feeds. It doesn't just see cars, it identifies them, maps them to specific lanes and calculates critical data like queue length and vehicle speed in real time. Second is the RL engine. This is how our system thinks. Built on the proven Sumo RL framework with a multi-agent architecture, our reinforcement learning agents analyze the data from the vision layer. They continuously learn the most optimal signal timing policies to maximize traffic flow across the entire city, not just one isolated intersection. Finally, the integration bridge. This is how our system acts. This custom software layer seamlessly translates the AI decisions into the precise data format that real-world data traffic controllers can understand, effectively bridging the gap between simulation and reality. This approach allows for real-time adaptability, making dynamic decisions every few seconds. It's a data-driven policy, ensuring the most efficient strategy is always chosen, and most importantly, it provides network-wide optimization, preventing the common problem of just shifting a bottleneck from one street to next. Our core innovation is the simulation to reality bridge. We are not just a simulation, we have built a deployable, real-world solution that is modular, scalable, and founded on robust, peer-reviewed frameworks. Now, to walk you through the technical architecture, we move to the next slide. As you can see from the main flowchart on the left, our architecture is designed for efficiency and real-time performance. Live camera feeds are processed by our vision layer using YOLO V8 and OpenCV. This generates real-time traffic data, which our integration bridge converts into a state vector, a simple set of numbers our AI can understand. This simple state vector contains the four metrics that we talked about in our dashboard: change in cumulative waiting time, average vehicle speed, negative total queue length, and traffic pressure differential. This is basically the throughput. This vector is fed into our RL decision engine. Here, we can select the right model for the job: a simpler DPU network model for a single intersection, or a more powerful PPO model for a coordinated grid network. The model issues an action command to the traffic light controller API, and we can monitor this entire system status on a live dashboard, which was showed first. Our technology choices were deliberate. We chose YOLO for its incredible balance of speed and accuracy on edge devices. We used the Sumo RL framework because it's a validated simulation environment that drastically cut our development time, allowing us to focus on AI training. For scaling to network-wide grids, we use PPO for its superior learning stability in multi-agent environments. In this case, when there are multiple junctions instead of just one, it doesn't just shift the decision to the next junction, it optimizes the traffic across the entire city, across the network of junctions. And as talked already, the art of an AI is the custom reward function. The agent is rewarded for positive outcomes like reducing vehicle wait time and increasing average speed. By constantly seeking this reward, it autonomously teaches itself the most efficient strategies to clear traffic. The technology stacks we used are here. A great idea is only as good as its execution. We have rigorously analyzed the feasibility of our project and have clear mitigation strategies for the key challenges. Our foundation is strong. We are building on a stable core. With the open source Sumo simulator and our flexible perception module allows us to easily upgrade our vision models in the future without a complete system overhaul. Looking at the table, for real-time performance, which is a medium risk due to model inference delays, we will use multi-camera fusion in deployment to get a complete view and have a smart fallback system that defaults to historical patterns if detection confidence ever drops. For integration and scalability, our standardized data pipeline pre-validated in Sumo, solves the challenge of translating vision data for the RL agent. For city-wide scaling, we have decided a distributed cloud architecture. Our highest risk is detection reliability, as adverse conditions like heavy rain or low light can impact accuracy. To counter this, our model is trained on a robust dataset, simulating these exact conditions. Once again, multi-camera fusion will provide redundancy, ensuring the system makes informed decisions even in pure visibility. So, what does this all mean for our cities and citizens? The impact is transformative. We are moving beyond rigid, static traffic signals to an intelligent, adaptive system that minimizes delays and ensures smoother traffic flow. The benefits are multifaceted. Socially, it means a less stressful daily commute and safer streets for pedestrians and cyclists through context-aware signal adjustments. Economically, we reduce fuel wastage, increase overall productivity, and make transportation more reliable for businesses. Environmentally, by minimizing idling and fuel wastage, we contribute to cleaner air and reduce noise pollution. And for governance, by minimizing idling and fuel wastage, we provide city authorities with actionable data-driven insights as well, laying the foundation for future smart city initiatives, which our smart dashboard is helping them with. Here's how our final prototype put together will be looking like, where the CCTV camera feed will be using YOLO to identify the number of cars on each lane and then sending in those parameters, which will bridge to give us parameters that are equivalent to what a Sumo simulation would be giving us. And these are junctions that we will be forming networks with and training our RL model on. And those can be as complex as how an actual city works as well. And RL takes care of taking the decision. And here are all the references that we have used. Thank you so much for the wonderful opportunity given to us.